Lab 27, Redox Titration. Introduction. You are a chemist working for a chemical analysis firm. A large pharmaceutical company has hired you to help salvage some products that were damaged by a small fire in their warehouse. Although there was only minimal smoke and fire damage to the warehouse and products, the sprinkler system ruined the labeling on many of the pharmaceuticals. The firm's best-selling products are iron tonics used to treat low-level anemia. The tonics are produced from hydrated iron 2 sulfate, or FeSO4, 7H2O. The different types of tonics contain different concentrations of iron 2 sulfate. You have been hired to help the pharmaceutical company figure out the proper label for each bottle of tonic. In the chapter Acids and Bases, you studied acid-base titrations, in which an unknown amount of acid is titrated with a carefully measured amount of base. In this procedure, a similar approach, called a redox titration, is used. In a redox titration, the reducing agent, which is Fe2+, is oxidized to Fe3+ by the oxidizing agent, which is MnO4-. When this process occurs, the Mn in MnO4- changes from a +7 to a +2 oxidation state and has a noticeably different color. You can use this color change in the same way you used color change of phenolphthalein in acid-base concentrations to signify a redox reaction endpoint. When the reaction is complete, any excess MnO4- added to the reaction mixture will give the solution a pink or purple color. The volume data from the titration, the known molarity of potassium permanganate solution, and the mole ratio from the following balanced redox equation will give you the information you need to calculate the molarity of the iron 2 sulfate solution. To determine how to label the bottles, you must determine the concentration of iron 2 ions in the sample from an unlabeled bottle from the warehouse by answering the following questions. How can volume data obtained from the titration and mole ratios from the balanced redox reaction be used to determine the concentration of the sample? Which tonic is in the sample given information about the concentration of each tonic? Materials. For this lab, you will need 2 250 milliliter beakers, a 400 milliliter beaker, 2 burettes, distilled water, a double burette clamp, 4 125 milliliter Erlenmeyer flasks, iron 2 sulfate solution, a 100 milliliter graduated cylinder. I also think you can benefit from a 10 milliliter graduated cylinder, 1 molar sulfuric acid, 0.02 molar potassium permanganate solution, and a ring stand and wash bottle. Follow your standard safety procedures for this lab. Procedure: copy the data table into your notebook. Clean 2 50 milliliter burettes with a burette brush and distilled water. Rinse each burette at least 3 times with distilled water to remove any contaminants. Label 2 250 milliliter beakers, 0.02 molar potassium permanganate and iron 2 sulfate solution. Label 3 of the flasks, 1, 2, and 3, and label the 400 milliliter beaker waste. Label 1 burette potassium permanganate and the other iron 2 sulfate. Measure approximately 75 milliliters of the 0.2 molar potassium permanganate and pour it into the appropriately labeled beaker. Obtain 75 milliliters of the iron 2 sulfate solution and pour it into the appropriately labeled beaker. Rinse 1 burette 3 times with a few milliliters of the 0.02 molar potassium permanganate from the appropriately labeled beaker. Collect these rinses in the waste beaker. Rinse the other burette 3 times with small amounts of the iron sulfate solution from the appropriately labeled beaker and collect these rinses in the waste beaker. So for this lab, I am trying to work inside this little white box so that you can really see color change. There were some complications with this. It was very difficult for me to get a good angle for titration. When I titrate, I like to use my right hand to control the stopcock and my left hand for swirling the flask, but I could kind of only get one arm in and not obscure the camera too much. So I actually overshot my titrations more than I would have liked. But hopefully when we do it in class, we'll have better luck because we won't be working within a tiny little box trying to get a good view of the color change. So here are our samples, both dry and before made into solution. Set up the burettes as shown in Figure A. Fill one burette with approximately 50 milliliters of the 0.02 molar potassium permanganate from the beaker and fill the other burette with approximately 50 milliliters of the iron 2 sulfate solution from the other beaker. With the waste beaker underneath its tip, open the KMNO4 burette long enough to be sure that the burette tip is filled and repeat this for the FeSO4 burette. You want to be sure you don't have any bubbles and that your solution goes all the way to the very tip. Add 50 milliliters of distilled water to one of the 125 milliliter Erlenmeyer flasks and add 1 drop of the potassium permanganate to the flask. Then you're going to set this aside to use it as a color standard for comparison later on in the titration. Record the initial burette readings for both solutions in your data table and add 10 milliliters of the iron 2 sulfate solution to flask number 1. In addition, you're going to add 5 milliliters of 1 molar sulfuric acid to the iron 2 sulfate solution. The acid will help the iron 2 plus ions from keeping them in a reduced state, so it allows you some time for your titration. So here are our initial readings from the burettes. Slowly add potassium permanganate from the burette to the iron 2 sulfate in the flask while swirling the flask, as shown in Figure C. When the color of the solution matches the color standard you prepared in Step 8, record the final readings of the burettes in your data table. So we're adding the 125 milliliter flask. We're adding to it the 10 milliliters of the iron 2 sulfate solution. And we're using the burette so that our measurements are very, very accurate. And now we're going to add 5 milliliters of our 1 molar sulfuric acid to this flask. And now we're ready to titrate. We're going to keep our color standard nearby so that we know what we're shooting for. So as I said before, I like to titrate by swirling with my left hand and using my right hand to control the stopcock, but I kept kind of getting my arm in front of the camera. I had a hard time finding just the right drop rate. You also want to be careful not to get any drops on the side, and I did because I'm leaning in at a weird angle. And as you can see, we actually overshot it a little bit. It's a little too intense, the color. It should be lighter than that. But we're going to record our data anyway. We're going to empty titration flask into the waste beaker, and then we're going to repeat this same procedure that was in steps 9 and 10 with flasks 2 and 3. So this is the adding 10 milliliters of iron 2 sulfate, 5 milliliters of the 1 molar sulfuric acid, and then titrating the potassium permanganate very slowly, drop by drop. And then after that, we're going to be sure that we clean up. So here's trial 2. And here I was fussing with this stopcock, trying to do a two-handed job with one hand so I didn't get my hands in the way of the camera, and I way overshot that color. That's like way darker than it should be. So here's our third trial. This one, I just went really slowly. See if we could get closer. Especially since I'm doing the two-handed job one-handed. And right about there, it's starting to change. And so I wanted to see if I could get one more drop, because that's a little undershot. That would have been perfect, but as you see, when I pull it away, I get one more on the side, and it runs down, and then it gets a bit darker. But right before that drop drizzled down the side, it was about spot on. So this was much closer. So analysis. Now we know our volumes used. Calculate the number of moles of potassium permanganate reduced in each trial. Okay, so we know that 1 milliliter is 0.001 liters, and we know that the molarity or concentration of our potassium permanganate was 0.02 molars, which is moles per liter. So we can just do this calculation and find that we had 0.00002 moles per milliliter. Now we know the milliliters of potassium permanganate that we used in each trial because we have the volumes right there below in our chart from our burette readings. So we have trial 1, trial 2, and trial 3. So we'll run these calculations. And there are our results. Calculate the number of moles of the iron ion oxidized in each trial. So in this case, we have our equation, and we're going to need to do some balancing, and we're also going to need to do some half reaction equations, which the lab rats are doing, but the junior lab rats are not doing. So we'll just kind of go through it slowly. Basically, we need to find the oxidation numbers involved with each of these components. And then we need to note that the iron is losing electrons, so it is oxidizing. We know it's losing electrons because it goes from a +2 charge to a +3 charge, and that is far less negative. And then if the iron is oxidizing, then the Mn part of the potassium permanganate is gaining electrons, so it is reducing. And we know that it's gaining electrons because it goes from a +7 to a +2, which is more negative, is a smaller number. So now we're going to take this half equation and look at the iron here, and this half equation, and look at the manganese over here. And that right there is a factor by which we need to multiply the iron portion, the oxidation portion of this equation. So we go ahead, get this equation balanced, and we need to consider these are our coefficients that we didn't have before. And there it is. So this is our new balanced equation. So how do we calculate the number of moles that we oxidized? All right, well, we're going to take our coefficients and use them to determine the number of moles based on the volume. Again, this is something that lab rats are doing, but junior lab rats really are not working on this type of equation yet. So this is about ratios. If our coefficient for Mn is 1 and for Fe is 5, then we just have to keep those ratios the same. So if we have 5 moles of the iron and 1 mole of the manganese, then if we change that molarity to 0.000042 for the manganese, what's it going to be for the iron? And it works out to 210. And then when we do our dividing, that's what we get. So here are answers: the number of moles involved and the number of moles consumed. So now, calculate the average concentration or molarity of the iron tonic. So how are we going to do that? Well, we know what it was per milliliter. So now we just need to determine what it is per liter. And there we are. If our concentration in our 3 trials was 0.00021 moles per milliliter, 0.00038 moles per milliliter, and 0.00012 moles per milliliter, we can convert those to moles per liter, which gave us our 0.021 moles per liter, 0.038 moles per liter, and 0.012 moles per liter. And if we take all 3 of those, add them up and divide them by 3, we get 0.02367 or 0.0234 moles per liter, which is the same thing as a 0.0234 molarity. Explain why it is important to rinse the burettes with potassium permanganate or iron 2 sulfate before adding the solutions. Hint, consider what would happen if each concentration, if it were added to a burette that had been rinsed only with distilled water. Okay, so this is something for the junior lab rats to understand for sure. So the reason that we rinsed with distilled water was to make sure that the burettes were very clean. But then we rinsed them again, if you remember, with the solutions we would be titrating. Why? Well, the concentrations and volumes are so small that even a drop of water could cause the results to be way off base. Even one extra drop of potassium permanganate causes us to way overshoot our titration. Conclusion. The company makes 3 different types of tonics: Ferrovide A, Ferrovide Extra Strength, and Ferrovide Junior. Which tonic is in your sample? Well, we can see the different molarities for the different tonics, and we know that our sample was roughly 0.0234. So looking at this, we could say that based on our average result of 0.0234 molar iron 2 sulfate, we could assume that we had a sample of the Ferrovide Extra Strength, because that's pretty darn close. But if we want to go based on our best titration results, the one that was closest to our color reference, we might suggest that we had a sample of Ferrovide Junior. And I happen to know the actual molarity of the iron 2 sulfate solution. And I will tell you, our closest titration was by far our most accurate. We were very, very close.